one of the advantages of having kids is that you can go into a toy shop and you can go and buy the biggest and most brightest toy in the shop and walk out and say, it's for my son. So this Christmas, asked the kids what they want for Christmas, and they come up with their various ideas. And so what Peter, who my son, came up with, he said he wants Lego, he wants Nerf guns, and he also wants one of these. So I thought that, I thought, right, that's the present he's getting. That looks like the most fun. Okay. Right, so just to tell you what this is, it's a little robotic car. It's got various parts of it. It's got a little processor on board. It's a little Arduino processor. It's got a tiny bit of memory, but enough to run a computer program on it. It's got distance sensors on the top, Bluetooth, infrared, and underneath it's got some line tracking devices. Okay, so it allows to check whether it's over a line or not. Okay, so having bought that for Peter for Christmas, at the same time over Christmas, I talked to my brother, who also works for a financial services startup, and so he was actually going on that because he's been looking at using machine learning in his company for improving it. So that made me think, right, okay, got machine learning, then I could go and read about it, but let's try to put it into practice. So the problem was, could I get something useful that would make this go better using machine learning? Okay, so that was the problem. Okay, right, so let me just show you how this works. So if I just set that going, oops, right. So it comes with various programs. So this is the program that came out of the box. So if I set that going, okay. So it will, out of the box, it comes very simple programs, and it's not bad. It will go mainly around. So the first thing that Peter and I did when we saw that was to say, that's great, can we make it go faster? So that's now the challenge. Can we get a neural network to learn how to go around the line faster than the basic algorithm that came out of the box? Okay. Right, if I just show you, okay, I've just got a few slides just to talk you through. So, this is the basic algorithm that the software came with. Okay, so we've got 3 line sensors. So if this sensor is over the line, then obviously it turns hard left, so it just does rotate. If that sensor is over the line, it just rotates that way. Otherwise, it goes straight on. So that's the basic algorithm to try and beat. Okay. Now, I'm going to tell you. I know quite a lot of you know quite a lot more about neural networks than I do. Okay, but I'll just like recap about neural networks, just to remind you, refresh your memories, and also tell you how I understand it. But neural networks take their inspiration from the way the brain works. Okay. So in the brain, it's made up of, I don't know, thousands, millions, I don't know if it's billions of neurons, but lots and lots of them, okay, all joined together in a network. And so this is a diagram of what a neuron looks like. So basically you've got a big blob here, which is the nucleus, and that receives inputs from these dendrites. So it's connected up to various other neurons. The inputs come into the nucleus, and then based on the volume of the inputs, then decide where to send the signal on. And if the signal is high enough, it will then send the signal on through this axon, which then connects it to the other nucleus using the axon terminals. So that's a very simplified, this is not a talk about biology, it's a very simplified view about the way a neuron works. Okay, it's more complicated than that, but this gives the inspiration behind the neural network. So a neural network, this is a very simple neural network, looks like that. So just like in the brain, you've got lots of neurons. So in a neural network, you've got lots of neurons here, which are then connected to the next layer of neurons using these lines. Okay. So here I've got 3 input neurons, and they're then connected to each of the middle neurons, of which I've got 4, and then I've got 1 output neuron. And so they're all connected in a chain. Okay. And so this then is like the nucleus of the neuron, and these are like the axons of the neuron, and then the dendrites are here as well. So that's how it sort of like tries to mimic how our brain works. Okay. The reason behind using a neural network is that it's to try and solve a class of problems that are very difficult to solve using procedural programming, such as things like image recognition, handwriting recognition, and it's to try and think more like a brain. Okay, we don't really understand how the brain works, but this is sort of like a starting point to try and get closer to how the brain works and try to use that in programming rather than procedural. Okay. So, just to give you a bit of the maths behind it. So the way the maths works is that given the set of inputs on the left-hand side, so I've got 1, 0.5, 0.2 and 0.8 going in, each of these connections has a weighting which decides how much it passes the input on. So my weightings might be 0.5, minus 2, 2 and 5. And so the way it works is it multiplies the inputs by the weighting and then produces another figure, that's total, which in this case is 3.9. It then has a bit of activation function, which is a sigmoid function in this case, which then works out how much to pass on. So it takes that, the 3.9, and converts it to a number between 0 and 1. So 3.9 is quite high, so I get a high number, nearly 1. And that then goes through the weighting and goes on to the end neuron, which does the same process. So you don't really, to some extent, the math in between is not important. The important bit is you take a lot of inputs on the one side, and then it does a bit of processing on the inside, and then works out what the output is going to be based on a set of inputs. And you can then check the output, and then adjust it. So if it's right, it's okay. But if it's wrong, you can then point in which direction is better, and it will then relearn, adjust all the weightings to then get closer to the answer next time. So by going back through the loop of constantly putting inputs in, checking the outputs, going back through, you can get it to get closer to the right answer. Okay, does that make sense? So that's the background to the neural network. So, the question is how to apply it. So, when thinking about how to make a better algorithm, I thought one of the things I thought would be good is to get it to learn from the past. So currently, the current algorithm just takes the current situation to work out what to do. So I thought, well, probably, if I tell it not just the current state, but the previous states, it could come up with a better answer about how to steer. So for example, I've got two situations. So on the one on the left, it's been off the line 2 steps in a row. So obviously, it needs to steer much harder right in that situation than the one on the right, where it's only just gone off the line. That's because it's slowly drifting off the line. That's a sort of a slight correction. Right. So that's just a theory. So that's what I'm going to try to test out. But by looking at the past, I hope it will come up with a better estimation. Okay. So, right, neural networks just take in numbers. They don't have any understanding about what they mean. So this is what my numbers are. If the line is completely to the left of my sensors, I'm going to call that a 0. If it's over the first sensor on the left, that's a 1. If it's between the two sensors, which in this case means they both fire, then that's a 2. Over the middle is a 3, and then between the two is a 4, and then you get a 5 and a 6. So you get a range of numbers, that's the input. I'll actually divide that by 6 to get a range of numbers between 0 and 1. This is what I put in. And then I interpret the output, which again between 0 and 1, that 0 means hard left, 1 means hard right, and 0.5 then comes out straight on. Okay? So that's then how I interpret the outputs. Okay? Right. Now, it may, when thinking about, is this a neural network a good thing to use for this? Because I'm sure I can come up with a set of procedures to get it go around the line faster than the standard one is. Okay? But part of it is just to see if it can be done, but also it's slightly more complicated than you might think. So if I tell my car to go straight on, actually, do I standing there to catch it? Thank you. Oh, great. That's all right. Thank you. That's fine. So if you notice, it didn't go straight. It went off to the left. Okay, and that's because it's actually quite cheap manufacture, and these wheels actually move around. So, based on their current configuration, if you look at them, they're not straight in line. But actually, sometimes goes off to the left, sometimes to the right. So it's not quite straightforward. But I need my neural network to cope with the fact that when it says turn left, it may turn more left than normal or more right than normal. So it's got to cope with that. And the other problem it's got to cope with is if I tell it to go hard right, it goes round quite nicely on there. If I put it down the carpet and tell it to go right, yeah, it struggles. It will eventually turn, but yeah, you can see it's struggling a bit. So yeah, though I could probably come up with some nice procedures to work at home on my floor, which has got 1 friction. When I bring it to work and try showing it here, you might find it doesn't work because the friction's different and therefore it's steering at a different angle. So it's got to cope with it. You know, there's a little bit of complexity in there.
Take your carpet.
That's right, I could bring my car in. That's the other option. It's very true. Right. So what's next? Okay, that's right. So what I'm going to pass with my neural network, that's my neural network. I've got 3 inputs, 4 hidden in the middle there, and then 1 output. My 3 inputs are the current position, the previous position, and then the previous position before that. And my output is the direction to steer. So that's what I'm going to interpret. Right. Okay, let me now I'm going to just show you what it looks like. So when you start the neural network, it's all randomized. So if I tell it to, let me just oops. If I tell it to go, right, then what will happen? It just goes all anywhere, because initially it's all randomized. So go, it just steers off the line, because when you first start your neural network, you randomise it. You've got no idea how it's going to behave. So what I've got to do, I've got to start training it. I'm going to use 2 types of training. One is supervised learning. Okay. So my supervised learning is basically, you're given a set of inputs, you know the answer in advance. So it's where you've got a whole nice training set, these inputs, that output. So for my training set, I'm going to use my current algorithm, which is, though it's simple, didn't work that well, it is actually very straightforward to program a whole lot of examples to train the neural network. So my current algorithm is if the input on the left, the sensor on the left is over the line, then turn hard left. If it's over the one on the right is over the line, turn hard right, otherwise go straight on. Very quick to program. So I can run that if I tell that to train. So it starts training, and so you'll see actually it's reporting out. It tells you the error, and that's because, like in neural networks, they're not memorising what the answer is. They're actually learning it, and so every time it gets a little bit better. But you never get a perfect answer. You're always trying to work out how close am I.